Welcome back to the Intro to Internal Combustion Engines. This lesson objective is to identify the air standard assumptions and the cold air standard assumptions used to model reciprocating internal combustion engines. When doing analysis of internal combustion engines, we can apply assumptions to make that analysis a little bit easier. So let's talk about the air standard assumptions, which can be found in your book in section 13.3, but I highly recommend writing these down regardless. So the first assumption is that the working fluid is a fixed amount of air modeled as an ideal gas in a closed system that undergoes a cycle, where we've eliminated the intake and exhaust of the working fluid. So remember, on the 4 strokes associated with a 4-stroke internal combustion engine, you have an intake and exhaust stroke. We've eliminated those strokes for the sake of analysis. And so now we have a closed system, and instead of air and fuel, we're just modeling the air only, and we can treat that air as an ideal gas. Well, you're probably asking yourself, so what? What does that mean? Well, first, it means we have the ability to use the ideal gas equation of state, of which there are many forms. This is just one. But more importantly, we have an ideal gas. That means the enthalpy and the internal energy are functions only of temperature. In this case, I've written it specific enthalpy and specific internal energy, but that remains the same. They're functions only of temperature. If you forget this, go back and review section 1.13. This is a very important factor. Now, just because internal energy and enthalpy are functions of temperature does not mean that the specific heats are constant. They are variable, and I'll show you this a little bit later on how you apply that. But this is a common error. The specific heats are still variable with the air standard assumptions. The second assumption is that all processes in the cycle are internally reversible. So what does that mean? Well, it means there's no dissipative effects such as friction and pressure loss, etc., within the processes. However, do not confuse that with isentropic. That does not mean that all the processes in the cycle are isentropic. To be isentropic, you must be both adiabatic and reversible. You will have irreversibilities due to heat transfer in the surroundings. Let's talk about how we model those. Well, the combustion process is modeled as heat transfer into the system, right? Instead of having a combustion in the cylinder, we're saying instead there's heat transferred into our closed system because we're modeling the working fluid just as air. So you're obviously going to have heat transfer into the system. So that is not isentropic, though it is still internally reversible. And you will have exhaust process that you model as heat transfer out of the system as heat rejection. So again, not isentropic, but internally reversible. Let's take a quick look at the reference data card. Recall when we're using the air standard assumptions, we are using air as the working fluid and we have variable specific heats. So we can use table 8 and 8E to find the specific internal energy, specific enthalpy, and specific entropy by looking up the associated values at the associated temperatures. Additionally, for the processes within the cycle that are isentropic, that have air as the working fluid, you can use table 8 and 8E to find the relative pressure and relative volume in order to solve for an unknown pressure or specific volume that you may not have. Let's review how to use table 8 very quickly. So here we have table 8, which is in metric units. So let's say our first temperature is 300 Kelvin. So we can look up the specific enthalpy, specific internal energy, both in kilojoules and kilograms, or the degree entropy in kilojoules per kilogram Kelvin. Additionally, you have these columns that show the unitless properties of relative pressure and relative specific volume. I recommend you look in the textbook if you don't remember what those are, and make sure you do the practice problems on how to use those relative pressure and specific volume. Now, if I have additional temperature, I can look up that temperature at the additional state at the end of some process, and I can find its associated values and use them in those equations. Additionally, looking at table 8E, if you are using English units, then you can find your temperature, this time in Rankine for state 1 and state 2, and you can look up their associated properties, their specific enthalpy, their specific internal energy, their degree entropy, and their relative pressure and relative specific volume when it's isentropic. Pay very close attention when you're using this table to the units. It's pound mass and BTUs. If you have foot pounds and you have slugs, you have to make sure you do the appropriate conversions. Next, let's talk about the cold air standard assumption. So in the cold air standard assumption, you have the same 4 assumptions that we used in the air standard assumption with the addition of 1 more. Okay, so it's ASA plus 1, and that 5th assumption is that the air has constant specific heats, but not just constant specific heats at 300 K or 540 Rankine because it's cold air. Okay, going back to our reference data card, you can see that we have constant specific heats, and now we have equations that when we have constant specific heats, we can use the differences in temperatures times the specific heat at constant volume or constant pressure, depending if you're trying to find the internal energy or the enthalpy. And we can use those equations to solve for these values. Additionally, you have the isentropic relations that you can use for the processes that are isentropic. To find the specific heats at constant pressure or constant volume, we can use table 7, where it has the ideal gas of specific heats of some common gases. It's important to ensure that you're looking at the right temperature and at the right gas, in this case, air. So at 300 Kelvin, we can find the CP and the CV in kilojoules per kilogram Kelvin. We can find the ratio of specific heats at 1.4. We can also use table 7E if we're using English units. Now, again, making sure that we've selected air. We're not using carbon dioxide or erroneously using carbon monoxide. We have to use the right temperature. Remember, we said that was at 540 Rankine. Well, wait a minute. This table is in Fahrenheit. So remember that the temperature in Rankine is the temperature in Fahrenheit plus 459.67, or roughly 460. So therefore, 540 Rankine minus 460 is 80 degrees Fahrenheit. So in order to get your specific heat at constant pressure or constant volume and your ratio of specific heats, which is 1.4, which should be the indicator that matches, because that ratio is the same whether it's English or metric units, that ratio of specific heats 1.4, we're coming in at 80 degrees Fahrenheit. It is a common error to use 530 because you think that's close enough. That's 530 Fahrenheit. That's way hotter than cold. You want to use 80 degrees Fahrenheit on table 7E. And again, remember the units. This is BTUs per pound mass. If you have slugs or you have foot pounds, you have to do the conversions. Okay, that wraps it up for this lesson objective. If you have any questions, contact your instructor.